Binary search. If you want to view these slides, they are posted on the Discord. If you go to this coding problems forum, there's a new feature in Discord, and then go to this problem set binary search. I have the slides, and you can gain access to them here. We're also going to go over these these 3 questions in the slides today, and then I have a couple of challenge questions that we won't go over, but you can do it on your own. So, binary search. How many of you have heard about the binary search algorithm before? Okay, a good amount of you. So, for those that have not heard about binary search, it's an algorithm that's meant for a sorted list. And it's used to find whether an element is contained in that sorted list and the location of that element.
Is that the same website that we used before?
Yes, that website was named after this algorithm.
Is the website back?
The website is still dead.
Wait, what?
What?
Yeah.
I did that. I DDoSed the site.
I literally did that because we had like a, we DDoSed it with sessions. I think that's why they took it down.
Actually, your streak.
I mean the correlation.
There's no way. That's crazy.
So it can be used to find the location of an element in the list in log n time. So as opposed to, okay, say we're given a problem. Given a list of integers nums and an integer target, return the index of the target in nums. If target is not in nums, return -1. So how would we do this? The naive way would just be to, say we're looking for a 7, to scan each element and see, okay, is the value a 7? No, 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 yes. And because we found the 7 here, we then return the 3. If we scan the entire list and then we see that there's no 7, we can return -1. However, what would be the time complexity of that?
Too much time.
True, but I mean, it's not super slow, but it's not optimal.
So it doesn't have to check one by one, correct?
Yeah, so if say a list was 100 long, it would have to check all 100 elements to see if something was contained within it. If a list was 1 million long, it would have to do 1 million comparisons. Now compare that to binary search, which we claim is O of log n. This means that log of n basically is the reverse of the exponent. So if say an input size is 2 to the power of 10, we're only going to have to do 10 comparisons. If input was 2 to the 100, we'd only have to do 100 comparisons. And 2 to the 100 is a massive number. So log n suggests that the algorithm is really, really efficient. And this is actually sort of the basis, this binary search algorithm is the basis of a bunch of search databases and having really efficient querying of data. So how does this binary search algorithm work? So we can start with left and right bounds. We know that if the target is somewhere in this list, it would be somewhere between these left and right bounds. So basically, it's somewhere in the list, right? However, the clever thing that we can do is because we know the values are sorted in this list, what's a good place to start? What's a good place to see, okay, here's my initial guess of where the element is. Where would you guess?
Middle.
Yeah, so the middle is a good place to start. And we'll see why later. So let's start in the middle. So we could do like middle between 0 and 10. Let's say that's 5. So let's say a middle is here. Now, a target is 7. We see that in the middle value is 10. What does that mean? Keep in mind that this entire thing is sorted ascending. If we see that this is 10, do we have to check any of these numbers to the right? No, because we know that's ascending. So we see this 10, we know that the answer is not on this right side. So we can eliminate this entire right side from a search. So now, instead of having to search this entire left, right, all 10 elements, we now only have to search these 5, 0 to 4. This makes sense so far?
You have to first sort it through a second.
Yeah, so this is, of course, if it was not sorted, if there was like a 7 over here, then this algorithm would not work. But because it's sorted, we can do this optimization. All right, so then we can just repeat that process again. what's a good place to guess?
The middle of that list.
Yes, the middle between left and right, which would be 2. So we set a middle there, and then we see a value at index 2 is a 4. What does that mean?
It's to the right.
Yep, so it's to the right of this middle. So it's either here or here. We eliminate that entire left side. We say, okay, we know that if there's a 7, it's not going to be to the left of the 4. So we can do that again. We have this left and right. And then we place the middle, in this case, it's sort of arbitrary where we place it, but let's place it where the left is. And then we can say, oh, this element that I'm looking at is a 7. We found a 7, so we can just return 3 as an answer. So that is the simple binary search algorithm. And the key thing about it is that whenever we do the step of choosing the middle and then eliminating a side, we reduce the space that we have to search by 1/2. So again, if it was the input was of size 2 to the power of 20, we do one of these rounds, and now we only have to search 2 to the 19 elements, then 2 to the 18, then 2 to the 17. So that's why it's so efficient. And this is the code to do that. So let's sort of walk through it. These are the bounds. The left is at, and this corresponds with the left and the right that we saw here. The left is at 0, the right is at the right end. And then while left is less than or equal to the right, so while pointers are not like, while the pointers, left and right pointers, are still like pointing at an element. It's not like they've crossed each other. We set a middle to be in the middle of the left and the right. So left plus right divided by 2. And that would be, if left is 0 and the right is 4, the middle would equal 2. 0 plus 4 divided by 2 is 2. If it was 3 and 10, that would be 13 divided by 2, round down, so that would be 6. So it places the middles in the middle. If the value at m is equal to a target, so that corresponds to this step that we did here. So if we're looking at a target, then we just return that index. So if m is pointing at a target, we return m. Otherwise, if the number that m is pointing at is less than the target, that was the case back here, right? M was less than, or 4 was less than a target of 7. So therefore, we can eliminate the entire left side. And that's equivalent to saying, okay, now have a new left side be m plus 1. And that's what we did here. Basically, making the entire left middle and everything to the left as irrelevant. And on the other hand, this would be if nums of m is greater than target. So then we eliminate the entire right side. We say we don't have to search the right side anymore, and a new right would be to the left of m. This code makes sense? All right. Anything that you want me to go over again? Okay. Yes.
Isn't the y at the left side is the m plus 1?
Yeah. So in this case, a middle will be pointing at 4, and then nums of mid would be less than a target, right? So we know that it's not mid. We don't have to. Mid is not a target, right? So therefore, we only have to search to the right of mid. So a new left would be pointing at the 7, because we don't have to. It won't be here. It won't be left equals mid, because we just searched this spot, so we don't need to search again. That answer your question? Any other questions? Yes.
How would the algorithm work if it was an odd list?
Yeah. So say like it was 0 and then 9. So left would be 0, right would be 9, and then that divided by 2, that would round down.
Okay.
So it would be 0 plus 9, sum of 9 divided by 2, that would be 4.5, round down, that would be 4. Yes.
So for this to work, the list has to be in order?
Yes.
Order? Okay.
Yeah, so if, say, it was 1, 3, 4, 7, 8, 7, that would not work.
Yeah.
But something like 1, 3, 4, 7, 7, 10, that would still work. It doesn't have to be strictly ascending, it just has to be, ascending.
Yeah.
Any other questions? All right, awesome. So this is a binary search algorithm. However, what we just coded is not extremely powerful. It works well for that one problem. However, there's other problems that use binary search that don't use that as a template. So if you've solved binary search problems before, you know that you're gonna get off by 1 errors, you're gonna get have issues with like infinite loops, all these problems. So it's really nice to have a single template that you can plug in and drop anywhere, and that's what I'm gonna be teaching you now. So instead of thinking about each index as having a numerical value, like for example, for that previous problem, we had numerical values of 1, 3, 4, 7, etc. Instead of thinking it that way, I want you to instead think of it as each index meeting or not meeting a condition. So, for example, we could say that the condition is the number less than 9? Is the value less than 9? And in that case, all these 5 will be false. Wait, sorry, greater than 9. So in that case, all of these will be false, all of these will be true. Does that theoretically make sense? I'll go into more detail later, but we have to, instead of thinking about it as values, think about it as condition. So, but this condition must be split into 2 sides. Everything to the left must be false, everything to the right must be true. If, say, there's a false over here, then a binary search template won't work. By default, a template will return the smallest index that meets the condition. So if we, so basically you see we have a bunch of trues on the right side, a bunch of falses on the left. Our algorithm, by default, will return the first true. There are 4 different places that we have to change, only 4 places that we have to change in a template. So that is the min possible answer. This is like, given a problem, what's the minimum answer that is possible? And that will be a left bound. On the other hand, we'll have a max possible answer. Given a problem, an input, what's the maximum possible answer for that input? Now, there is a caveat here that I'll go into a bit later, but we may need to add 1 to that, but I'll get into that later. And then we have this is condition met. This is what I'm talking about before with converting all the numbers to be falses and trues. This will take you from the world of numerical values, or sometimes not even numerical values, sometimes it's something different, into falses and trues. And then here we either return L or L minus 1, and I'll get into that a bit later. So let's see how that applies to a separate problem. So given a list of integers nums and an integer target, return the smallest index I, such that inserting target at index I will result in a sorted list. So let's go through a couple examples. Say I want to insert 9. Where would I insert that? Which index?
Index 5.
Yeah, so if we sort of place a 9 right here and then shift everything over, like shift all this 10 to 14 over, then we'd be left with 1, 4, 4, 7, 8, 9, 10, 10, etc. What about 11? Where would we place that?
After 6 polygon.
Yeah, so it would be 7. Because then we could place, we move all these over to the right and then place a new 11 here. So 10, 10, 11, 11, 13, 14, 14. What about 10? Where would we place that? Yep. So note that we don't want to place it at 6. Even though this would still result in a sorted list, we want to return the smallest index I where it's possible. This makes sense so far? Alright, so let's go through a template. What is the minimum possible answer? Where is this, given any input and any target, what's the smallest index that we could place it at? 0, exactly. And let me just copy this over real quick so that I don't have to go back to the slide.
Goes to 10.
Yeah, that's fine. We can deal with it.
It's curved.
Shut up.
We're doing that.
Okay.
This is gonna,
Too small, I can't read it.
it's not gonna go on
No,
YouTube anymore.
no. Okay, so, yeah, so the minimum possible place that we could place a number is index 0. And then say if you test that, like given this input, no matter how small we make the input, the right place to place it will be 0. Like negative 100, we still place it at 0. So that is a min possible answer. What about a max possible answer?
10.
So would it be 10? What if a target was 100? Yeah, so we actually place it at 11. Because you can think of it as like placing a 15 here. Right, we're not going to place it at 10 because that would mean that we place the 15 here and then shift the 14 over right. So a max possible answer would actually be, how do we calculate it if we're given the array is called nums? How do we calculate?
Length of the right.
Plus.
Exactly. Well, is it nums.length or nums.length plus 1?
Oh, wait, no, it's, length already gives you plus.
Yep, so it's nums.length.
Yeah.
This is a maximum possible answer. Any questions so far? Alright, so now this is the hard one. What is a condition? What will turn, and the way that I like to think about this condition is what will turn this into, instead of values, a list of true, falses, and then trues, where the first true will be positioned at where we want to place it. Yes?
Duplicates?
What do you mean by that?
4, 4, and 10, 10.
Well, it won't always be that, because let's say that we want to place a 7, or let's place a 9, right? Or actually, let's place an 8. It's not going to be at like where the duplicate is necessarily. So again, let's say the target is 9. And where do we want to place the 9 again? 5, correct. Now what condition will make it so that the first true will be positioned at that 5?
Like the numbers, the value of the arrays, like maybe something like smaller than a target, right?
Yeah, just flip it. So, what I heard is this. The nums, and then at index m, remember that the condition will always be sort of in reference to m, since that's what the number that we're currently looking at. You said is smaller than, but remember that we want the right side to be true, so it should be greater than target.
Or equal to.
Actually, and why or equal to?
Because it could be the same value.
Yeah, remember that if a target is 10, we don't want to place the 10 over here. We want to place it here. So in order to make the first true at that first 10, we have to do greater than or equal to. Now that's a really important step. Does that make sense to everyone? All right, awesome. And just let me know if you have any questions. So that is a condition. Now we have two options. We can return L, and returning L will return the first true. Or we could return L minus 1. And this will, instead of returning the first true, it will return the last false. What should we want to do?
L.
Yeah, we just want to return L. So, we solved the problem. So let's just walk through how this is working. And let me, I don't want to, Let me just quickly copy paste this code over here. Actually, no. Let me do it on over here. Okay. Let me be smart about things. So, oh, this is actually the exact one. Okay. Okay. So, we start with a left at the 0, a right at the 11. Can you all see that? So then we go to this first m. M will equal left plus right divided by 2. So 0 plus 11 divided by 2, what is that?
5.
5.
And a half.
Yes.
5.
So m will be here. Next thing that we do is we say, is nums of m greater than or equal to target? So is this greater than or equal to target? Yes. So then what we do is we set right to be m. So right is now here. And then we basically eliminated this entire side from the entire question. We repeat that process. We set m to be 0 plus 5 divided by 2. What is that? Two. And then we say, okay, is this is nums of m greater than or equal to target? No. So what do? We set L to be m plus 1. So now a search size is this range. We repeat that process one more time, so our new m would be here, and then we do, is m nums of m greater than or equal to target? No. So then we set a left to be here, and then we've now escaped our while loop, because this while loop only continues while left is less than right. So then our left is at 5, and then we return that 5. This makes sense to everyone? Now, there's some key parts that, if it's sort of confusing, like why is right just m and not m minus 1? Why is this left m plus 1 and not just m? I just say to just deal with it, because it's, you don't really want to get into the weeds of why this is the case, but it works to find the first true with the last false. So, let's go through this. Let's go through one more problem. And this is, now you might think, how can we use binary search to solve this problem? So given a non-negative integer x, return the square root of x rounded down to the nearest integer without using the built-in square root function. Now this is weird. We haven't given a sorted list. So how does binary search apply here? Remember that the only thing that a binary search template needs is some values, is falses and then trues. So if we think about the square root of x rounded down to the nearest integer, we can instead reframe it as a question of like, okay, there's some numbers where if we square them, they will be less than x. But past a certain point, once we hit a certain point, once we can then, all the numbers multiplied by themselves will equal or be greater than x. So we can, that is basically the same thing as saying we have a bunch of falses and then a bunch of truths. And let's say this is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So like say if x was, in this case like 17, well, no, in this case, it would be, yeah, 17. So, if we square 5, then this will be 25. That'll be greater than 17. If we square 4, that'll be 16. But if you see every number greater than 5, if we square that, it'll be greater than 17. Every number less than 4, if we square that, it'll be less than 17. So it's a set, it's falses and then trues, and we have a boundary. And therefore, we can use the binary search algorithm to solve this. So, if we're thinking about, like, say we're given a number 17, and say we don't know, what square root is. We could say, you know, as a min answer, what's a good min answer that's possible?
0.
Yep, 0. Why not go for 0? What about a max answer? What's like a reasonable, max answer? Yeah, let's just go with x. So in this case, it's n, since I did not rename the function. Now this is n plus 1. I'll get into why that is later. Ignore that for now. Now, a condition, you know, let's just go with what we said earlier. You know, if a number, let's call this m, if m times m is greater than or equal to x. Well, in this case, let me just call it n. That way, you know, if we have, well, let's go greater than. That way, you know, everything that we know is not, if we square is greater than n, that's going to be a true. Everything, if we square is less than an n, that's going to be a false. And then I'll work through this on the board since it's a little bit confusing, but yeah, we'll just go through it. And then, so now, we're looking for the nearest integer, the square root of x rounded down to the nearest integer. So if it's 17, then what is the answer for this? Square root rounded down. 4. Because 4 times 4 is 16, so it's a little bit over that. So if we go the other way, square root of 17, if we round down, it'll be 4. So, based on that, should we return m or L or L minus 1?
L minus 1.
L minus 1. Yep, so let's go through how I made all these decisions. And I think the most important thing here is, why did I choose a condition to be m times m is greater than n? So if we try to do, and this is honestly just a trial and error process. Like, there's not a really good way of doing it, but you just have to test it on the whiteboard and see, you know, what's a consistent way that I can get the answer. So if we instead did m times m is greater than or equal to n, then say if we had 16, this would be a true. So in this case, we're going to return, L would be positioned here. But we already saw earlier that if we had n equals 17, that this would be false. So then L would be here. But the answer in both cases should just be 4, right? So that sort of contributes to why I chose m times m is greater than n. And in this case, now when n is 16, this 4 will still be false. So you just have to draw it out on the board, test out the condition, and see if that gives you the result you want, of where either the last false is always at the answer, or the first true is always at the answer. That makes sense? All right, so now why did I choose equals n plus 1? Why didn't I just say equals n? And this is an edge case. You know, you hate to see those, but the template always ends up with L at the first true. However, say in this case, if there's no true, it'll end up at the last false. Therefore, when we do L minus 1, we end up returning the second to last false instead of the last false. So instead of returning 1, which is the last false, we'd be returning L minus 2. Yeah. Or 0. But if we add 1 to the answer, then there will always be a true, so therefore we're always going to be returning the last false when we return L minus 1. Do you want me to go over that again, or do you understand that? Yeah, the gist is, if you are returning L minus 1, you might have to add plus 1 to the right side. That's the gist of things. So, now that I've given that lecture, and you can stop recording now, Shabbat.